In our fourth video for chapter 3, we're going to take a step away from nomenclature and look at structures of some of these compounds and how they affect physical properties, things like boiling point and solubility. So let's start with alkyl halides, right? And this looks familiar. We've seen this information or similar to it already, right? What is an alkyl halide? We take an alkane, pluck off a hydrogen, and replace it with a halogen, something from group 17. And as the new bit of information here, right, is as we take that halogen and make it larger, right, so going down group 17 from fluorine all the way down to iodine, notice that the bonds here, right, become longer. These are bond lengths expressed in angstroms, which is 10 to the minus 10 meters. So that's getting longer, and a longer bond is a weaker bond. And that's because the electron density of the orbital is decreasing as we increase the volume or the size, right? That orbital overlap from the sp3 hybridized orbitals that are participating in the bond. And that's going to affect our physical properties, right? That's something to keep in mind. What about alcohols? Okay, those somewhat resemble water, right? And alcohol is ROH. If you think about water as being HOH, you can see how that structure about oxygen is similar, keeping in mind that oxygen is sp3 hybridized, right? One of your orbitals is overlapping with the s orbital of hydrogen, another one with the group from carbon in your R group, and then you have two lone pairs that are in sp3 hybridized orbitals, tetrahedral geometry, a little bit of a hot spot there in the potential map from those two lone pairs. If we switch from an alcohol to an ether, notice we just switched that H to an R here, okay? It's pretty much still the same. Right? We just changed hydrogen. It's now another sp3 hybrid orbital over here. Still that hot spot there in the middle from the two lone pairs on oxygen. Okay. What about amines? Okay. Now we know that ammonia is NH3, is sp3 hybridized, right? And amines are the same, be it a primary, secondary, or tertiary amine. They are all sp3 hybridized with, again, a lone pair in a hybrid orbital, giving us a hot spot on that potential map. Okay, and then any of these bonds are overlapped with an sp3 hybrid orbital from nitrogen and an sp3 hybrid orbital from our carbons in the case of these alkyl groups, or an s orbital in the case of hydrogen. Right. So that's a little bit of structural information. Chances are you were probably familiar with all that information. But we wanted to review it again as we jump into 3.9 here to see how those functional groups affect physical properties of molecules. And those are called non-covalent interactions. Okay? These are interactions that are weaker than covalent bonds, right, between molecules. So let's look at that, starting with boiling point. Okay? And we've covered some of this information in general chemistry in the past, right? What's going on when we have a boiling point? Okay? We've got these non-covalent interactions, these forces, intermolecular forces, right, that are keeping our individual molecules close to one another. If we're thinking about a boiling point, we're thinking about a liquid. And there's a direct correlation between those intermolecular forces and the boiling point itself. The greater the attractive forces, the higher the boiling point, the more energy you need for these things to leave the liquid phase and enter the gas phase. Keeping in mind that the boiling point is the temperature at which the liquid vaporizes and becomes a gas, right? A normal boiling point is the boiling point at 1 atmosphere. You might recall that from Gen Chem. And if we're thinking about intermolecular attractive forces, we know there are 3 types, right? London dispersion, dipole-dipole, and hydrogen bonding. Yep. We've got London dispersion forces first. If you forgot about those, they're sometimes also called van der Waals forces, though van der Waals is really the sum of all forces. It's the weakest of all the attractive intermolecular forces. and it's the result of two spontaneously induced dipoles, which happens because electrons are always moving. So if you think about it as a sea of electrons, you might get a temporary partial positive or a partial negative, and then that will induce dipoles in neighboring molecules, but it's just a temporary instantaneous thing. We typically just see this in alkanes, where we have only carbon and nitrogen. They're neutral, they're nonpolar, all nonpolar bonds throughout the molecule. So there's no significant differences in electronegativity. There's no significant distribution in the charge. But if we're thinking about alkanes, right, and the probability that we get a spontaneous induced dipole, at the area of contact is important, because the larger the surface area, the greater the chance these things have to interact with one another, and the greater the chance for an induced dipole. So look at these boiling points. Right? As I go from methane to ethane, propane, butane, right, all the way up to octane, so from 1 carbon up to 8 carbons, these things are getting larger. They have stronger London dispersion forces, right, greater induced dipoles, right, and therefore higher boiling points. So make sure you've got this point in the bottom there in your notes. The greater the surface area of a molecule, the higher the boiling point. Okay? Or conversely, right, the smaller the surface area, the lower the boiling point. So the size in terms of the number of carbons is definitely important, but there's another thing that's important as well, okay? And that is branching. Because if I have molecules with the same molecular weight, so notice here I'm looking at 3 isomers of pentane, okay, C5H12. So that's the key thing, right? The molecular weight is arguably more important, but if we're looking at things that have the same molecular weight, how branched the molecule is significant because it affects the area of contact. Right? You can think about it like 2 circles versus 2 lines. If I have 2 lines, they can have a lot of area of contact, versus 2 circles, they can't interact all that much. Okay? So pentane, which is in a straight line, okay, it can have some stronger London dispersion forces, notice a higher boiling point, than if I start to branch some methyl groups off there. And the more branched something is, okay, then the lower the boiling point becomes. Okay? So the higher the degree of branching, the lower the boiling point. Okay? So if you want to maximize your boiling point, you want something to be high molecular weight and straight chain. Okay? So that's London dispersion forces. What about dipole-dipole interactions? Yep. We're not going to see those with alkanes where we have just carbon and hydrogen, but if we have nitrogen in our molecule and an amine or oxygen or a halogen, right, these things are more electronegative than carbon. So those are going to give us an induced dipole, and then we're going to have dipole-dipole interactions. Okay? Whereas London dispersion forces are from a temporary induced dipole, dipole-dipole interactions are from a permanent dipole, which is what this figure here in the middle is showing. That comes from polar bonds where we have a partial negative and a partial positive. And that causes our molecules to align themselves to maximize those electrostatic interactions. Okay? But as long as you know that, then you're in business, because the rules that we talked about with London dispersion forces still hold. Okay? So dipole-dipole is stronger than London dispersion. But if we're looking at 2 things with dipole-dipole, it's still things that are heavier that have stronger London dispersion forces, or sorry, dipole-dipole in this case. So if it's larger, right, more atoms in the molecule, or lower branching, those have higher boiling points, which is summarized right here. Okay. Notice as I replace this carbon in the middle with oxygen, now my boiling point goes up. Same thing down here. Okay. But then you'll notice it goes up again with switching from an ether to an alcohol. Okay? And the fact that the amines are higher than the ethers as well. So it's clearly not just a polar bond, right, that's going on with dipole-dipole, but hopefully you realize that that OH or NH is significant. Because yes, it's a polar bond as well, but it's a special kind of polar bond. That's where we have hydrogen bonding. Okay. So we'll circle back to hydrogen bonding in just a second, but before we do that, right, to finish dipoles, let's think about alkyl halides. So when I'm putting a halogen, something from group 17 on a molecule. Okay. So if I have an alkyl halide, and so I've got a carbon chain and then I've got a halogen somewhere on it, I have to overcome the London dispersion forces in the alkyl part of the molecule, where all the carbons and hydrogens are, and dipole-dipole forces, wherever the halogen itself is. And what's key to note is as the halogen increases in size, both those kinds of interactions become stronger, which is a key idea. As you go down group 17, your halogen becomes larger. Both of your interactions become stronger, okay? And that's because as we go down group 17, we have already mentioned it in this video, these things are getting larger. Okay? So if it's a larger electron cloud, that is a larger contact area, okay, which we said is significant. When we were just talking about branching, contact area is significant. It's also a looser hold on the outer electrons because they're further away from the nucleus in that halogen. That means that the electron cloud is more polarizable, right? Notice this slide labeled polarizability. That means the electron cloud can be more easily distorted to create an induced dipole, okay? It's more polarizable. Because those electrons are less tightly held, it's easier to create induced dipoles. So look at these comparable boiling points, right? You see a big jump up as you go from hydrogen to a halogen, because that's when we go from just London dispersion to dipole-dipole. But then as that halogen gets larger, moving left to right from chlorine to bromine to iodine, your boiling points continue to go up. Okay. So the larger the halogen, the more polarizable it is, the higher the boiling point that molecule has. Another key thing to know for dipole-dipole. So what about hydrogen bonds? As promised, you should remember from Gen Chem, right, the three things that hydrogen is bonded to have hydrogen bonding, that's oxygen, nitrogen, or fluorine. Hydrogen bonding is the strongest type of non-covalent interaction, right? But the key thing is it's still a non-covalent interaction, an intermolecular force. Hydrogen bonding, while the strongest of that type, is still weaker than any covalent bond. But you will notice it gives us a huge difference in boiling point, right? Methane and water, similar molecular weights, right? But methane with no hydrogen bonding, boiling point of -167 C. And water, as we know, boiling point of 100 degrees Celsius, just because of the hydrogen bonding. Okay. And therefore, when we have hydrogen bonding, we see the highest boiling points that we have for molecules. And if we want to maximize our hydrogen bonding, notice this figure up top, right? We want them to be able to arrange to one another in a linear format, right? Put that hydrogen in a straight line over to the lone pair that's attracting it in nitrogen. Right? Maximize that hydrogen bonding. Okay. And therefore, we see how it arranges when we're able to put a bunch of water molecules together. So you're probably familiar with hydrogen bonding from Gen Chem already as well. But one thing to pay attention to is amines. Okay, look out for amines. Now, amines still have hydrogen bonding, but you will notice that they have lower boiling points than alcohols. Okay, and that's because nitrogen is less electronegative than oxygen is. So the hydrogen bonding, while present, isn't as significant as it is in things like water. Okay? But if we're looking at classes of amines in and of themselves, hydrogen bonding is stronger in a primary amine than it is in a secondary amine, okay? Because they have different dipole-dipole interactions. And we don't have any hydrogen bonding in a tertiary amine, because while the amine is present, you have to have an NH bond to have hydrogen bonding, and there's no hydrogen on a tertiary amine. Okay? So primary amine, right? Larger hotspot there, stronger hydrogen bonding. Right? Secondary amine, smaller spot, less extensive hydrogen bonding. Another easy trick I tell students to look out for, just think about NH2, right? 2 hydrogens, more hydrogen bonding than just an NH. Okay? Easy little trick to remember it by. And this hydrogen bonding has a huge role in life as well, right? Hydrogen bonding is what holds protein together in things like alpha helices and beta sheets. Right? When you denature a protein, typically you're breaking that hydrogen bonding. It's also what holds your DNA together. Okay, so you have to look out for DNA, like things like DNA intercalators, right? Carcinogenic compounds, they can insert themselves and interrupt that hydrogen bonding. Okay. And this hydrogen bonding is also important in life and structures as well, because compounds with similar shapes and properties can share similar physiological activities. If they have the same type of bonding in the body, right, as they go into like, enzymes, substrates, etc., in those active sites, if they're triggering the same kind of bonding, they may have the same effect in the body, right? They may also have no effect or a adverse effect, right? Biochemistry is a tricky beast. So what about melting points? Okay. Similar information to what we already got from boiling points. We use that as an example property. Okay, the only other thing to look out for with melting points, right? It is influenced by how things pack together, how close they can pack together as you go right from a solid to a liquid. So the only other tricky thing to look out for with melting points is that if you have an alkane with an odd number of carbons, they pack less tightly than it would if your alkane had an even number of carbons. Due to these repelling methyl groups shown there in red that kind of point right at one another, your odd numbered alkanes have weaker intermolecular attractions. Okay. So if it's an even number, they have a tighter FET. It takes more energy to break the lattice and melt the compound. Okay. But other than that, as long as you're familiar with all the information we talked about in boiling point, you'd use it to predict the same information for melting points. So we finish by talking about solubility, another topic we discussed in general chemistry that we'll expand upon here. You should remember the rule like dissolves like, meaning that a polar compound will dissolve inside a polar solvent and a nonpolar compound will dissolve in a nonpolar solvent. Water and hexanes used as the example here, but we'll see a ton of solvents throughout this and next semester. What we're interested in any case, regardless of the solute in the solvent, is a process that's known as solvation. This is really what controls like dissolves like. If I have a polar compound, it will dissolve in water because it has a dipole, right? Meaning it has a partial positive and a partial negative that will interact with the opposite partial charge from water. So you see how those water molecules orient themselves around the polar compound, and that allows it to dissolve. That process is known as solvation. It's an interaction between the solute and the solvent. Okay, but if this polar compound in here was actually a nonpolar compound like an alkane, it wouldn't be able to interact with those partial charges, and it would actually interrupt the water molecules themselves in the solvent trying to interact with one another. It would interrupt that hydrogen bonding in water. So that's why we don't see nonpolar compounds dissolve in polar solvents, because it reaches a higher energy. We don't want that. We're always trying to go to lower energy. But if I had a nonpolar solvent, like hexanes, then the London dispersion forces are similar to one another, so they can mix. Okay. And alkanes, for example, always nonpolar. So they'll only ever be soluble in nonpolar solvents. Okay. What if we have an alcohol? Alcohols are tricky because I've got that OH, meaning I have a polar group and it might want to go into a polar solvent, but the size of the alkyl group is solvent, and is important. And the key idea, something to jot down, is that alcohols are typically soluble up to 3 or 4 carbon atoms for every OH. Okay, so methanol, ethanol, propanol are soluble, but as you get larger than that, we start to lose solubility in water. Okay, because the longer the alkyl chain gets, it's occupying a greater and greater percentage of the molecule. So we're becoming less like an alcohol, more like an alkane, and we're losing our solubility. Okay? the carbon character increases, our solubility in water decreases, which we can see right here, okay? And oxygen can drag about 3 carbons into water, be it in ether or in alcohol. Okay? So make sure you've got that in your notes, right? Notice down here, we're too much like an alkane, so we're insoluble. And we finish with amines. Okay? Again, the molecular weight, the size, the classification are all important. The lower molecular weight amines with fewer carbons attached to them are soluble in water because the nitrogen can hydrogen bond with what's in the solvent. Okay? And primary amines, right, where we have an NH2, are more soluble than secondary amines, where we have an NH, are more soluble than tertiary amines, where we just have the nitrogen. Tertiary amines can be soluble in water because they can hydrogen bond with the solvent themselves. All right, but there is a big drop-off with tertiary amines. Okay? So know that, right? Primary, most soluble, followed by secondary, followed by tertiary. Okay. And in terms of the alkyl halides, alkyl fluorides are the most soluble because they can form hydrogen bonds in the solvent. Okay, remember, hydrogen bonded to oxygen we talked about, nitrogen we just talked about, fluorine. That can also form hydrogen bonds. So alkyl fluorides can be soluble in water. Okay? But as we switch to alkyl chlorides, alkyl bromides, alkyl iodides, they lose their solubility in water. And as we increase the size, they get less and less soluble. Okay? So lots of rules, lots of things to pay attention to, all based on the structure, but know what we talked about for boiling points of all those different structures and solubility of all these different functional groups, because those will continue to affect our principles of reactivity that we'll get in chapter 5.